Já tady nevidím? Ne.
Ani nebylo.
Nebylo.
Tady ho uvidíš.
Dobrý, to je dobře.
Počkej ještě to. No, už jdeme. Tak si můžeš.
Okay, so be welcomed in the first live stream of a histological practical training. We are in histological department with our lecturer Andrea, who will participate in this practical training. We are planning to demonstrate all slides of the urinary system for electron micrographs which belong to this system. At the end there will be embryological part, so according to my meaning, because it was on Monday in Czech, it can be about 4 hours of this video streaming. You can ask your questions by live chat. We will answer them with a short delay, but not long, so I think it will be really online, and I hope that you will like it. In this first page you can see a slide of kidney. It is a kidney stained by hematoxylin and eosin. I hope that you will look at it alone as soon as possible, but now I'd like to ask Andrea to take it and to demonstrate it, because she was preparing for this.
I don't know if preparing is the right way.
Volume.
I don't know if we can increase the volume much. I don't know. Can you hear me right now? Because it's maximum we can do right now. I know we are wearing masks and stuff, but can you answer me if you can hear me properly? Hi. Hi.
Hi.
If you don't know me, my name is Andrea. And we can hear you well. Okay, thank you very much for the answer. So today we're going to explain we're going to explain urinary system. The volume is very low. I can hear you well. Some of you can hear me well. Some of you are writing that the volume is very low.
Can help.
Yeah, maybe headphones. Put on headphones, maybe that will be helpful. So maybe that's a problem on your computer somehow. Okay, but let's start. The first slide is the kidney. It's slide number 55, I guess. It's written right here. It's 55. And you already know the kidney and the basic structure of the kidney from anatomy, I guess. But the histology is kind of like different. So basically what are we going to have on our slide is this kidney. And you know, kidney is like composed of some parts. I'm sorry, I'm going to try to write on it. Okay, so this is the kidney, and of course the parenchyma of the kidney is around something called sinus. So this is the sinus, renal sinus. And in this sinus, we can see there are some parts, there are some structures. So we can find here vessels, veins and arteries, and also some collecting renal system. I guess I can say it like that. The renal pelvis, and collecting stuff like calyces. And of course, loose connective tissue with adipose tissue here and other stuff. And the kidney is composed kidney itself is composed of medulla. Medulla is organized into some parts called pyramids. So this is one pyramid, this is the second pyramid, this is the medulla, the third pyramid here, and the pyramids are like 8 to 18. So yes, these are the pyramids of the kidney, composed of medulla. And about the medulla, we can see cortex. Yeah, cortex. So this is the cortex right here. Cortex. Cortex is going between the medulla in some columna. I don't know if my pronunciation is right, but
Renal columns.
columns. So renal columns. Columns? So
Yeah.
I'm sorry, guys.
It's,
I'm always teaching Czech students, so I'm not really used to teach English-speaking students. So sorry about that, but yeah, the columns. So the cortex is about the medulla, and it's creating columns between the medulla pyramids. So what are we going to see in our slide is that we're going to probably see one pyramid, maybe not whole pyramid, but some part of pyramid, and the cortex, which is about the pyramid. So this is probably something we're going to see through microscope, and probably some part of callus right here. Okay, so let's move on to the microscope, and let's see. Okay, you will be able to rewatch this later, of course. It's possible. Probably it's going to be saved on this channel, fix it. Okay, so now we're looking on the slide. This is the kidney. And we have some cortex, medulla here. We're going to describe it later. But what is about the whole kidney is a capsule. So at one side you can see a capsule right here. I'm going to write it like the renal capsule. It's somehow like this. I tried to draw it, but like you can imagine, I'm going to put like the focus on the capsule right now. And this capsule that is around the kidney is made of irregular dense connective tissue. Yeah, so this is the capsule. Irregular dense connective tissue about the kidney. Right about the capsule, which is made of dense connective tissue, there will be some adipocytes and loose connective tissue around here. So that will be the adipose capsule. But you cannot really see that right now. There are just some erythrocytes, and that is due to preparation of this slide. So this is just artifact, I guess. But you can see pretty well the capsule of the kidney. So once again, dense irregular connective tissue about the kidney. Okay, but how are you going to distinguish medulla and cortex itself? So, cortex, which is like, of course, right under the capsule, the cortex contains something called, I don't know if it is the right word, the renal bodies. Corpuscles.
Renal corpuscles, maybe.
Corpuscles. This is the right? How to write it? Yeah, renal corpuscles. Or renal bodies, I guess that's the right name. So these are the renal bodies, small renal bodies. We're going to describe them later. They have some parts, but these bodies are typical for the cortex. So when you find something like this, little circles around here, you can say, okay, this is the cortex. So the whole cortex is somehow like this. everywhere where you can find the renal bodies, there's the cortex. On the other hand, we can see some parts here which don't contain the renal bodies. So you can see a whole big part here, the place right here, where you can't see these renal bodies. So this is the medulla. And this is probably, like this is probably the one pyramid, or one part, or a small part of a pyramid. Maybe not whole pyramid, but just a little part of it. Yeah, just a part of one pyramid. And medulla is going to the cortex through things or the cords that are called striae.
Striae medullaris
In
in Latin, and medullary rays.
Medullary rays, yeah, thank you. Medullaris, striae medullaris, or medullary ray. So this is the medulla. We cannot see here any renal bodies. And these are medullary rays that are going right to the cortex. Medullary rays, like here. Do you understand? So, is this clear to you right now? You would be able to distinguish cortex from the medulla. Yeah, so this is the medulla, and this everything around here, which contains renal bodies, is cortex. Yes, okay, thank you. Sevda, I don't know if I pronounced it right, but thank you for the answering. Yeah, Katerina, thank you. So this is the cortex. Okay. So I'm glad that's clear. If we're going back to the macroscopic point of the view right here, those striae, those rays of medulla, which I was drawing right there, will probably go like this to the cortex. Yeah, I'm doing it right, like this? Kind of, okay. Yeah. Okay, and each stria or each ray is dividing the kidney into the lobules, small lobules. So there are many small lobules that is the kidney divided into. A complicated sentence for me, but okay. I hope you understand that. And if I said it somehow wrong, it's okay, right? It's okay.
Everything is perfect.
Okay.
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 Maybe you can add, if you are speaking about lobules, there are also lobes,
Yeah.
which are represented by a pyramid and neighboring cortex.
Yeah.
So, in fact, our slide is one lobe.
Yeah, so this is
Yeah.
one lobe. Pyramid of medulla and cortex above, it's one lobe. Okay. So we're going back to the here right now and the chat. Okay. So, and right now we are going to describe the renal body or the corpuscle, renal corpuscle. So we're going to find some pretty one here. The most beautiful corpuscle here. I don't know which one, but some of. Yeah, probably. What do you think? I think it's pretty. These two are pretty enough to describe them. Well, yeah. Okay. Yes. Okay, so this whole structure right here is a renal body. You already know that. It's in the cortex, of course. There are some other structures around. We're going to describe them later. But they are just like, if you know right now, they are tubules of the nephron. So you know from the renal bodies there is some tubular system, and these structures around the renal corpuscle or the renal body are tubules of the nephron, right here around. Okay, so let's go back to the corpuscle, renal, and the renal body itself. Renal body is composed of two parts. One and two parts. The first part is a structure called glomerulus. Glomerulus is a net of capillaries. So glomerulus is made of capillaries. It's just like it looks like this. This is a very nice picture. So this is the glomerulus. So some arteries, we cannot really see the arteries here, but afferent artery. Oh, my pen is broken. No. Okay. Should be fine right now. Afferent artery is going to the renal body, and it's making capillaries. So these are the capillaries right here, these spaces. You can see even erythrocytes here. So this is one erythrocyte, another erythrocyte. Here is another erythrocyte. You can see they are very much eosinophilic. These are the erythrocytes, and so there are many spaces here, and these are the capillaries. So the glomerulus is made of capillaries full of erythrocytes right here. I don't know if the signal is okay, or can you see us right now? Is everything fine? Because our internet connection isn't really nice today. I don't know why, but you can refresh it. I don't know if you can see us right now. Yeah, it's going? Yeah, okay. Probably your internet connection is better than ours here. Everything is fine. Okay, so sorry for this misunderstanding. So let's go back to glomerulus. Okay, so the renal body is made of glomerulus. It's the capillaries. We're going to explain the structure of the glomerulus later. And the renal body also contains something called Bowman's capsule. Bowman's capsule. And Bowman's capsule is a capsule, so it has some layers around. And the layers are two layers here. And the first layer is, I need some other color. So, for example, I don't know, orange. The first layer of Bowman's capsule is parietal layer. Parietal. And this layer we can see right here all around the renal body. And you probably can see what it's made of. It's made of simple squamous epithelium. So parietal layer is simple squamous epithelium. Squamous epithelium. So that's a parietal layer. And we have another layer of Bowman's capsule, and that is called visceral layer. So visceral layer. And the visceral layer is somehow special because you can see right here in this net right here, there's just not the capillaries, but there's many other cells right here. And you know the capillaries you have like one capillary right here. This is the capillary. This is erythrocyte in the capillary. And the capillary itself is going to have some endothelial cell right here that is protruding to the capillary. This is the nucleus of endothelial cell protruding into the capillary. And what is doing the visceral layer is that is made of special cells called podocytes. And these are very important special cells. And what are these cells doing is that they are sitting on the capillaries. So they have their own nucleus. They're sitting on the capillaries and they're like hugging the capillary. Yeah, this is my capillary and I'm sitting on it and I'm a podocyte. And they're creating a structure that is called filtration membrane. Yeah, is that right? Yeah, they're creating filtration membrane. Yeah, once again, sorry for my grammar. I don't know what I'm doing right now, but okay. Filtration membrane is the structure they're creating together. So the capillary together with the podocyte are creating filtration membrane that is very important, and we're going to see the filtration membrane in the electron microscopy right after. But we need to like how to say rozlišiť? Distinguish. Sorry, how to say? We need to distinguish them also in the light microscopy. So how are we going to do that? Is that we can find some good capillary here. For example, right here, this is the capillary. Yeah, and this is the erythrocytes in the capillary. And the one nucleus that is protruding to the capillary like this, you can see that it's in the capillary, right in the capillary, in the lumen of the capillary. This is probably the nucleus of the endothelial cell. Endothelial cell. This is probably I don't really know. It might be podocyte, but yeah, it's protruding to the capillary. I guess it's the endothelial cell. And the nucleus of a cell that is sitting on the capillary, it might be this one, or it also could be these nuclei here, or this one probably. This might be the nuclei of the podocytes, because they are sitting on the capillaries. So this is how you're going to distinguish them from endothelial cells. Okay, so we're going to find some capillary, and the nucleus that is protruding is probably the endothelial cell, and the other one that are sitting right on the capillary, they're probably the podocytes, which are creating filtration membrane. Okay, but that's not all. Yeah, you see this structure right here. There are endothelial cells, podocytes, and there are some other cells that are very special to the renal body, and they are called mesangial cells. Mesangial cells. Mesangial cells are special. They are kind of like macrophages in the renal body, but special macrophages. So its function is to phagocytose. So the main function is phagocytosis. You see right here there is a filtration membrane right here, and we're trying to create some urine and stuff. So there are much of stuff going through this filtration membrane, and we need to clean it. So these are the mesangial cells for. They're trying to clean the filtration membrane right here. So the main function is phagocytosis. Also, they're able to create matrix, and it's also, of course, called mesangial matrix. matrix, mesangial matrix. So they're just not like only capillaries and cells here. There is also some kind of tissue around. So, and it's called mesangial matrix. And also what they do is they contract. They're able to contract. So contraction. So they can regulate the lumen of the capillaries. So they can squeeze them and dilate them, constrict them, and do stuff with them and control like the blood flow through the capillaries. So 3 main functions of the mesangial cells right here. And how are we going to find them? Is that these cells haven't got contact with capillary. So they don't have contact with capillary. So, and they are very eosinophilic. Like all macrophages are eosinophilic, so also these cells are eosinophilic. So this is why they are pink right here. Accidentally, I did it, but yeah, okay. So they are very much eosinophilic, and they don't have contact with capillaries. So probably this cell right here would be mesangial cell, or this cell right here in the middle of nowhere. Or this cell here with very eosinophilic cytoplasm, and or here, well, these are the very pretty mesangial cells. But what's important for you right now is to distinguish the podocyte and endothelia cell right here and how it's working. So what's the purpose of all of this? You probably already know what's the purpose. And the purpose is to create the primary urine, the primary filtrate. And what is happening is that the blood is filtrated from the capillary to the some space called the space between Bowman's capsule, and this space is called Bowman's space.
Or urinary space.
Or urinary space.
Yeah.
And this space, you can see, like, I can write it right here. Bowman's space or urinary space is between the parietal and the visceral layer. And we can draw it like this. This is the Bowman's space. But this is really what we can see from the light microscope. But we know there is some space between the podocytes and the other parts. So you can really describe Bowman's space also right here, how I'm drawing the lines. But we were going to see that on the picture of electron microscope. So when you're going to describe it in the light microscopy, just draw it like here. This is the Bowman space. And this is the space where we're going to have a primary urine filtrate, which is going from the blood flow through the filtration membrane to the Bowman's space between the layers. Is that clear? Are you catching up with me? Is there something I need to repeat, or is it everything okay and clear? I think it's fine. I need to wait a little bit because there's a delay, like 5 seconds or 10 seconds, but okay. Yes.
They say yes.
They
Clear.
say everything is clear. Okay,
Yeah.
so I'm going to show you right now how is this going to look like on electron microscopy, right here. Okay. Okay, that's fine. Right here. So this is, of course, the capillary. Not K, but C, capillary. Capillary. And capillary on the other side. And this is you can see it right here, is described lateral process of an endothelial cell with pores. And this is very important for the filtration membrane. These endothelial cells, which are right here lying like they're doing the layer of the capillary, or how can I describe this? It's not important. The endothelial cells have something called pores. And you probably, and that was also my case, I was thinking about this, like the lateral processes are connecting together, and these are two endothelial cells, and this is the pore, but this is really not the correct situation. I was thinking about it like this earlier, but it isn't right. It's actually like that this is the one endothelial cell right here with the nucleus, and the pores which I like drawing right now here, these blank spaces are in the endothelial cell like this. Yeah, this is the nucleus, okay? And these are the pores. So they are in the cell, the pores, okay? Hopefully you understand this situation. So really, this is the section, so you're probably not able to see it from this section. It's not fenestrated endothelium. It's very different. It's endothelium with pores. Fenestrations are like holes with a diaphragm inside. But this is only the pore. This is just really a hole. There's nothing in it. These are only the holes through the endothelial cell. So it's not fenestrated endothelium. And it's very important to remember on the test, oral exam, and everything for life that the endothelial cells in the glomerulus have pores.
Maybe I can say that these pores are called in some textbooks fenestrations without diaphragm. Yeah, that's sometimes problem. It's quite long, so I prefer, and we all here in Prague prefer pores instead of fenestration without diaphragm. Yeah.
Okay, thank you. So let's go back. So these are the pores of the endothelial cells, and these things right here, which I'm drawing, are parts of the podocytes, small parts of the podocytes, because podocyte itself, I'm going to show you on the presentation so you can visualize that better. I don't see chat right now, but okay.
Go
More.
And here.
I like this picture. It's very pretty because you can see here is the nucleus of podocyte, and podocyte has got primary processes like this and secondary processes called pedicels. I don't know the pronunciation. Pedicels. Okay. And you want to show this picture or this picture? This picture is very.
This is higher magnification.
Yeah. This is very pretty picture, so you can see it right here. This is the podocyte with nucleus. These are the primary processes right here, and these small ones are secondary processes, the pedicels. And you can imagine it like that. There is not just one podocyte that is sitting on the capillary itself, but there are many of them. And the secondary processes of the podocytes are connected to, not connected, but they are just like this. Like this is one podocyte, and this is the second podocyte, and they're just like, I don't know how to say it, but yeah, this is the situation, what's happening. So I'm going to explain it like this on the electron microscopy. The situation is like that, this is of course the secondary process, but probably the secondary process of one podocyte. Let me label it A, and this is the secondary process probably of the second podocyte here, and this is another probably once again the apodocyte. So they're just like A, B. These are the secondary processes of maybe 2 podocytes, 3 podocytes there. Yeah?
Yeah.
Probably. Okay. So, and what is happening? Podocytes and of course endothelial cells of the capillaries are epithelial cells. And you know epithelium has its own basal layer or basal lamina. I can say it like that, basal lamina. And basal lamina is composed of lamina lucida and lamina densa. Yeah, and these, so we have basal lamina. You know that from the general histology, basal lamina. And it has got 2 parts, lamina lucida and lamina densa. Oh, it's quite dark. I don't know if you can see it, but probably yes. And the basal lamina of the podocytes and basal lamina of the endothelial cells fused together. So we can see lamina lucida of the endothelial cell, lamina lucida of the podocyte, and this dense stuff here are lamina densae fused together. So, and this whole structure right here, the endothelial cell, like the pores, the fused basal laminas together, and the podocytes is something called filtration membrane. So this whole structure right here is filtration membrane. And filtration, of course, is going from the blood here. There is a blood in this capillary right here. So from the blood to the space that you already know, the space right here. And this is the Bowman's space right here. So this is something, this space right here, this is too small. This is something that we cannot really describe on the light microscopy. We could only see the big Bowman space around the glomerulus, but this is also Bowman's space that is between the capillaries, between the podocytes, and this space contains primary urine or primary filtrate of the blood. Okay. So just remember the pores, they are important. The fused basal lamina, that is right here. This is the fused basal lamina. And the urine is going around the processes of podocytes. And these processes are together connected with something, something called, I should say, it's a diaphragm. It's a basic diaphragm here that is connecting podocytes together. So between the podocytes there is a diaphragm between podocytes. And this diaphragm contains protein called nephrin. Very important protein here. And also remember that the basal lamina here contains also some proteins which are important. So these proteins together create a barrier between blood and the Bowman space. And what is important also to know is that in basal lamina, in lamina densa, there is a collagen number 4, and in lamina lucida there are other important proteins like heparan sulfate,
Yes.
This doesn't look pretty. I'm sorry, but yeah, probably you can read it. So collagen number 4 and heparan sulfate and the nephrin in the diaphragm. It's very important for filtration membrane to do its job, because heparan sulfate, nephrin, and also some protein called podocalixin. This is not that important, but you should remember at least heparan sulfate, collagen number 4, and nephrin. These three are important. Heparan sulfate, podocalixin, also nephrin are negatively charged. So these three guys right here are negatively charged. And this charge is very important for the membrane, because if you know, most of the proteins in the, I shouldn't write it here, but like in the blood, there are some proteins in the blood, and they are also negatively charged. So what's going to happen is that this negative charge right here in the membrane, on the filtration membrane, won't let the proteins leak to the space. So no, not happening. Yeah, this is not happening. So this negative charge is very important for the filtration membrane, once again, because when there is some inflammation in the kidney, the pedicels, the secondary processes, are going to fuse together. They're going to fuse together, and this negative charge is going to cancel in the inflammation, in the setting of inflammation, and these proteins can leak to the Bowman space, and you're going to urinate proteins, a lot of them. So that's not cool. Okay, we should probably move on. So, is that everything I should mention in the filtration membrane? I think that's clear.
I think so.
Okay, look for the... You're doing amazing, sweetie. Thank you. Ľubožnácko. Aj. Dobre. I'm confused right now. Okay, so I'm back. So, what was here right now? We ended with the primary urine in the Bowman space. So once again, this is our Bowman space and primary urine. And what now? You know how much urine the primary filtrate, how much primary filtrate you're going to produce in the per day. It's like 180 liters per day of the primary urine. So I'm sorry. What you need to do, you need to absorb it. So there is in fact a size and charge dependent barrier function. Yeah.
Welcome, Roxana.
Oh, Roxana. Okay. Yeah, that's real.
She will help us.
Yeah, thank you very much, Roxanne. Thank you. Yeah, and Lukáš, yeah, you're right. 1.8 liters per day. So you need to absorb that back. You don't want to urinate that much, you will be dead. So you need a system of tubules to absorb that. And the system of tubules, which is doing its job in the kidney, it's called nephron. So nephron is a primary unit of the kidney, and it's very important. It has got some parts. So I'm going to describe it in the presentation. I don't know where. Yeah, here's my presentation. So this is the nephron, primary unit, and the nephron itself, is composed of some parts.
Maybe we can comment these numbers. The last is really correct.
Yeah.
Yeah.
The last.
180, not 1,000.
Yeah.
Not just 1 liter. Yeah.
180 liters per day. Yeah. I was like, okay. So, we're back. So the so the primary unit of the kidney is nephron. And nephron is composed of some parts. The first part, we have described it earlier, is the Bowman's capsule. So this is the first part. of the nephron, the Bowman's capsule. The second part is proximal tubule. Proximal tubule. It has some parts. Some part is convoluted, some part is rectal. Striate. Striated. So it's like the okay. So I'm going to call it all like proximal tubule, but you know it's somehow like striated. Some part is striated, some part is convoluted, but it's like not important right now. So the proximal tubule. The next one is the loop of Henle. Loop of Henle. Henle's loop. The last one is distal convoluted tubule. So distal convoluted tubule or distal tubule itself, I guess, distal tubule. So the nephron has Bowman's capsule, proximal tubule, loop of Henle, and the distal tubule. And we have something called collecting ducts here, or collecting tubules, I guess, collecting tubule right here. But this is not a part of the nephron. So this is not a part of the nephron. Yeah, it's very important structure. We're going to describe it. You need to distinguish it on the light microscopy, but it's not a part of the nephron. It has very, like not very, but somehow different embryology podcast. I don't know how to say it, but it was developed somehow different than the nephron. Nephron is developed from the other structure than the collecting tubule. Do you understand me? I hope. Yep. Yes. But what's important right now? You need to distinguish Bowman's capsule, of course, you can find it. Proximal tubule, the loop of Henle, and the distal tubule. You need to distinguish these parts of the nephron. And how are you going to do that? Is that you need to find, you need to distinguish the cortex right here. And you see the proximal tubule and distal tubule is mostly in the cortex. Macula densa, we're going to describe it later, but we're going to describe it. Don't worry. So in the cortex, there is a proximal tubule and the distal tubule, mostly located. And in medulla, we're going to look for the loop of Henle and the collecting tubule right here. So first we're going to look in the cortex, and we're going to look for the distal tubule and the proximal tubule. So let's see. Right here. Okay. So right here we can see like everywhere renal bodies. We certainly are in the cortex of the kidney. So I'm just going to somewhere here. I'm going to look at it more closely. Yes, I'm here. More. I need to see that. And yes, I can see it pretty clearly right now. And this is the renal body. And you can see on one side of the Bowman's capsule, which we described it earlier, that there is something going right out of the Bowman space. And this is the beginning of the proximal tubule. So I'm going to add proximal tubule. And this pole right here, this is a pole. It's called urinary pole. Urinary pole. And of course, if we have a urinary pole, we're going to have some other pole on the other side of this structure. And that is a vascular pole. Vascular pole. But that vascular pole is so small, we really cannot see it somewhere here. We just see the glomerulus with the podocytes and the mesangial cells, but we really cannot see where are the vessels coming through to the glomerulus. So probably the vascular pole should be somewhere on the opposite side of the urinary pole, somewhere here. We can show it somewhere else. So I'm just going to skip right like here. Don't worry about the things. I'm going to delete it. But yeah, this is somehow pretty. This is the urinary pole. It's the pole where the urine is coming out. And this pole right here, when you see there's like connection, this is the vascular pole. Vascular pole. Is that clear? Okay. So I'm going back right here. So, and you already probably know, so this is the proximal tubule, and all of these tubules here, which I'm drawing like this, these are the parts of convoluted proximal tubule. This is the proximal tubule here. This is proximal tubule. There is some blood, but that's just artifact. Don't worry about that. There is some proximal tubule, and you can see there are some cross sections through the proximal tubule, and this is also the cross section of the proximal tubule, and there are some longitudinal sections. So this is probably some like longitudinal section of the proximal tubule. So these tubules here all are proximal tubules. And proximal tubules have cells, are made of epithelial cells, and this epithelium is a simple columnar or cuboidal epithelium, cuboidal or columnar epithelium. Okay, so proximal tubules contains simple cuboidal or lowly columnar epithelium. And these cells are cool. I like them. Because these cells are big. Yeah. These cells are big. So sometimes it happens that these cells are like 20 to 30 micrometers and have like the nucleus in the middle of the cell. And so sometimes it happens that when you want to have a section through the proximal tubule, it's very likely you to sect like right above the nucleus or under the nucleus. So sometimes you can see that you're not able to see nuclei here, but they're there, of course. Each cell has its own nucleus, but you cannot see them because these cells are too big. You're not able to see nuclei all around the tubule. Also right here, this is the cross section. And you can really see nucleus here, 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 but there is a blank space and you're not able to find nuclei. So this is pretty much normal. It's a normal state. It's not that nuclei are missing, but they're just not there because of the section. So don't worry about that much. But what's also important for these cells need to transfer ions. Ions? Ions. I knew that wasn't right. These cells need to transfer ions. And how are they going to do that? You already know that the ion transporting cells need some structures for that, of course. So these cells of proximal tubule have the basal labyrinth right here. You know the basal labyrinth, there are just invaginations of the basal membrane, basal labyrinth, and they also have microvilli on the apical surface. So microvilli, basal labyrinth, these microvilli create the brush border, brush border on the surface, brush border. And this basal labyrinth in the base of the cell contain pumps. Pump it. Okay. So, but you know that the pumps, ion pumps, need energy, and this energy is made, well, like the mitochondria made energy. You know that. So these cells of proximal tubule need mitochondria, and a lot of them. So basically, I'm drawing this cell blue, but it's very, very eosinophilic because it contains, wow, this is very eosinophilic because it contains a lot of mitochondria. So only nucleus is basophilic, of course, like always, but the whole cell is eosinophilic because of the mitochondria. And what's also happening here is that there is another cell of proximal convoluted tubule, or the proximal tubule itself, right here next to the proximal, the other cell, I'm sorry. And what we can see in the electron microscopy, not in the light microscopy, but in electron microscopy, is that these cells are together connected with interdigitations. Is that correct?
Yeah.
So interdigitations. That I'm going to end it like this. It's okay. Okay, so they love each other. They love each other so much. There is so much love in here. They're like almost fused together. I'm not going to say it, but like interdigitations between these cells. So you really cannot see like the borders. You cannot see the borders of the cell or the surface, the lateral surfaces around the cell. It's impossible. So, if you want to describe these cells, these are columnar, cuboidal or columnar, lowly columnar cells. They are eosinophilic, of course, eosinophilic. They are big. They have got brush border on the surface. You can see it right here. Brush border on the surface. Yeah. They have got basal labyrinth. So they can transport ions, and they have got pumps, ion pumps in the basal labyrinth. A lot of mitochondria, so they're eosinophilic and they are big, so you cannot see all the nuclei here, but they're there, of course. Is that clear? I hope that's okay. But yeah, that was the proximal tubule. So the proximal tubules, here, here, here. And of course, you need to distinguish them with the distal tubule. And the distal tubule is right here. This is one section through the distal tubule. This is another section from the distal tubule. Here. Oh, and we can see like the longitudinal section right here. So these are the distal tubules, and you can already see some differences. If you know how to distinguish proximal tubule and you now look for distal tubule, you can see really some differences right now. So, of course, these cells of the distal tubule are smaller. You can see it right here. They are smaller, and you can see all the nuclei around the tubule. So it's also a simple, mostly simple cuboidal epithelium. You can see all the nuclei. These cells are smaller, and they're not that eosinophilic as proximal tubule. So they're not that eosinophilic. They are still eosinophilic, but less. and they don't have a brush border on their surface. They also have a basal labyrinth, but they don't have a brush border, but they do contain microvilli. One microvillus here, there is another, the third one, but these microvilli on the cells, on the apical surface of the cell, don't create brush border. So there are just lonely microvilli there. So, and there are some photos of electron micrography here. Yes, very well. Oops, sick. My chat is missing. So what can we see right? Sorry. I need to move it like here. So what can we see right now? This is the proximal tubule, and this is the section right through the part where we don't even see a nucleus. It's buffering. We're buffering. No.
I don't see anything.
It's something with your net connection. I know all the people
No,
right now are
No, here is okay.
all people right now are watching Netflix and stuff. So the internet is overpopulated right now. So maybe that's the case also at my home. The internet is not going right. It's fine. Okay, thank you, Martin. So this is the picture from electron microscope. Okay, and this is the proximal tubule. So what we see right here is that we don't see a nucleus because these cells are too big. You remember I was describing them earlier. It's okay now, thank you. It's good. So I'm glad it's working. We don't see a nucleus right here. These cells are too big that we're not able to see the nucleus. It was somehow like this. This is the section through.
No,
But maybe like yes. Yeah, I can see these are microvilli. So this is the case of this section, like here. So what are we going to see? We can see microvilli on the surface. So these are the microvilli on the surface, many of them, and they're creating brush border. And also we can see many mitochondria here, many of them. So this is why this is the case that the cell of the proximal tubule is so eosinophilic. So eosinophilic, you can see it right here. Many mitochondria. And this structure down here is of course basal labyrinth. Right here. I don't know, this is the, IP, basal labyrinth. Okay. So many mitochondria, basal labyrinth, brush border, some vesicles for the transportation and stuff. So yeah, this is how it looks like here.
Yeah.
Okay. And we also have, oopsick, I did it again. We also have a picture from distal tubule, and you can already see some differences. We can see a nucleus here. So this is our cell of the distal tubule. This is the nucleus, like this. And this is the case. So we can see the nucleus right here, and we can see small microvilli here, but they are not creating a brush border. Yeah, guys, this is very important. It's not there is no brush border here, but there are some mitochondria, many of them, of course, also many mitochondria. So this cell of this tubule is also eosinophilic. But if you want to compare the cell of the proximal tubule and distal tubule, of course, the cell of proximal tubule is going to transport more ions. It's going to be more active. It needs more energy, the proximal tubule. So it's doing the thing, the job. Yeah, but distal tubule is very important. I don't know if it's important to describe the aldosterone. Yeah.
Aldosterone, no.
Yeah.
If you started.
Yeah, I started it already. The distal tubule is very important because in the basal labyrinth, it contains a very important pump. It's transporting sodium potassium pump. So what it is doing, it's like going to these cells of distal tubule are going to absorb sodium. This is the blood. Okay, the blood is going here, and the urine is of course here on the other side. Hello from the other side. Okay, and we are going to absorb sodium to the blood, and we're going to excrete potassium to the urine. And this pump is how to say, like function due to a hormone. Yeah, it's dependent on the aldosterone, because aldosterone is making this pump active, I can say. So this aldosterone is making you absorb more sodium. So what is aldosterone doing? You're going to have more sodium in the blood. You're going to excrete potassium. So in the blood, you're going to have less potassium. And of course, with the sodium, the water is going right after the sodium. So what's the consequence of these things is that you're going to higher the blood pressure. And you already probably know that aldosterone is made in adrenal glands in the cortex of adrenal glands. So this is important. Remember that, yeah. Distal tubule is not doing that much, but yeah, it's dependent on aldosterone, and aldosterone is a hormone which is very important. It's created in the cortex of adrenal gland, and it's making you to higher blood pressure. Yeah, so you're absorbing more sodium, and you need a pump, and you need some energy for that. So that's why the distal tubule is eosinophilic also, and it has got many other pumps here, but this pump is the most important here, I guess. Okay. So you probably would know how to differentiate these two, yeah, proximal tubule and distal tubule. And what? Jo. Tak jsem mohla něco najít. We're talking about that right now, that between these tubules, they're not just like the nephrons in the kidney and the capsule and stuff, but between nephrons and between renal bodies, there is also a tissue. So we will what? Actually,
I don't know what do you want.
We were describing the proximal tubules here and distal tubules, but that's okay. There is like these cells are sitting on the basement membrane right here around, but there is also a tissue around these tubules. A loose connective tissue. It's small, you cannot really see it. You can see it right here. There is tissue, loose connective tissue all around the tubules. Yeah. Interstitium. Titium. Interstitium. I'm sorry. So this interstitium is made of loose connective tissue right here. And this loose connective tissue contains capillaries also. So there are some capillaries, and these capillaries are fenestrated capillaries. And we can see them, this is too big, but here, maybe. This is a capillary right here, or this right here. So the spaces where you can see very eosinophilic erythrocytes. When I'm going to do this with the microscope, you can see them blink, the erythrocytes right here. So these are the capillaries which are fenestrated in the interstitium. So yes, we have on the one hand we have glomerulus with capillaries with pores, and on the other hand we have interstitium with the capillaries, but they're fenestrated. So please don't confuse that. Yes, if there's going to be some questions, if you can find fenestrated capillaries in the kidney, and many of you will think, okay, glomerulus have capillaries with the pores, so it's not correct. But yeah, it's correct, because we can find fenestrated capillaries in the interstitium of the kidney. So yeah, that's the case. So okay, so we can distinguish proximal tubule with the distal tubule. And now let's move to other tubules here. We're still in the cortex, and you already know we're going to be looking for the loop of Henle and the collecting tubule right in the medulla. So we're back in the medulla. And we're going to look for the other tubules here. So you probably already know that the loop of Henle has its thick descending limb, or thick part, and thin part. And the thin limb of loop of Henle is going to be it's going to look like vessels. So it's going to be, there's going to be simple squamous epithelium in the thin limb, and the thick limb is going to look like the other tubules that we described earlier. So the thick limb of the loop of Henle is going to look much like proximal tubule or much like distal tubule. Yeah? And the thin limb is going to look like a vessel, and of course it doesn't contain erythrocytes in it. So it's going to be a vessel without erythrocytes. I guess I can say it like that. But okay, here we are in the medulla. So I'm going to focus more here. Yeah, we clearly are in a medulla, and I can describe these as thick segments. Probably no, not yet. Yeah, that's collecting duct. I need a little help with this right now. You see, I'm also confused in this part. But yeah, first, that's the thin.
Yes.
Okay, let's focus more. Yeah, that's look. Okay.
Must be.
This one. This is the fin. I can see it right here. So we're going to start with the thin segment of loop of Henle. This one right here. We can see that epithelium is simple squamous epithelium. So this is the thin segment of loop of Henle. So there is a simple squamous epithelium right here, and I'm trying to find some thick segment right here, but it's, which one? I'm sorry.
It's like distal, let's say.
Yeah, but this
one.
This epithelium is somehow very similar to the distal tubule. So I'm going to draw it green. And this is probably the thick segment. So thick ascending, because it looks like a distal tubule. Thick ascending. So, you don't have to worry about that much. Just like look for the medulla and try to find the thinnest epithelium here. If you find a tubule with the simple squamous epithelium and you can see there are no erythrocyte in it, you can say that's probably the thin segment of loop of Henle. And when you find some segments which have got cuboidal epithelium, it looks like distal tubule. Yeah, we can probably say it's a thick segment of loop of Henle. Thick ascending segment. Yes? I don't know if we're able to find...
And the vessels
yeah?
are here with these erythrocytes.
Yeah, we can see vessels here. And what do we need to know about them? Say?
No, we need to know that they are so-called vasa recta, that they accompany Henle's loops. They cooperate with them by reabsorption of water and ions. And in this picture, in this slide, we can distinguish them clearly and without any problem, as they have got erythrocytes inside. But some slides haven't got so many blood inside, so then this recognition isn't so much easy.
Yes.
What do you do?
Nothing, just like
I think
doing myself.
that we need a short break early, but let's finish description of a medulla.
Yeah, and then we're
There
going to
are
have a break.
also there are vasa recta, where is Henle's loop or loop of Henle, and where is also collecting tubule and duct.
Yeah, so wow, this is very pretty. So, and collecting ducts. Oh, sorry, collecting ducts, ducts or tubules look like somehow like this. So you can see columnar, I can say.
It depends on the size. This is quite proximally, so this is collecting tubule, where epithelium is still cuboidal, and deeper in medulla near the papilla will be higher cells, and we can call it collecting duct.
Yeah, and these cells, it's not very much like seen in here, but they're protruding to the lumen a little bit. You can see it protruding to the lumen, and you can also see lateral surfaces here. You can see this line, and this line is also right here. So you can see the lateral surfaces of these cells. So this is
because
there aren't those interdigitations between the cells. These cells of collecting duct are important because they contain aquaporins. These are pores which are transferring the water. I can write and talk at the same time. Porine. Like this? Can write it here. These are the I don't know it. Pores.
I think without this E, but it's quite good.
I need to improve my English, but okay. Aquapores. That doesn't matter. Let's have a break right now, but I'm just going to tell you this. These aquapores are here in the cells of collecting tubule, and these are transferring the water here, so transferring water, and are dependent on the one hormone, and you probably already know this hormone, ADH, antidiuretic hormone, which is produced in the hypothalamus. And from hypothalamus is going to hypophysis. And from hypophysis is released to the blood, to the stream, and antidiuretic hormone, of course, it's somehow activating the aquaporins, pores for the water, and the water is then absorbed back to the bloodstream. So this is how it works. Okay, I think it's time for a break right now. So we are going to meet here in 30.
Yeah.
Yeah, 30. 2:30. Uh,
2:30. We must say Central European time because we know that you are worldwide. Some of you have got another time now,
yeah,
so it's necessary to be like here in Prague.
yeah. So we're going to in 10 minutes probably. Yeah,
Yeah.
in 10 minutes. Okay. Hopefully we're going to meet soon. Ba-ba-ba-ba. Tak. Hello, hello. Can you hear me? Is everything okay right now? Hopefully we're back. And I need some answers to be sure that I'm not explaining histology to nobody. It's probably okay. Yes. Yes, thank you. Thank you. So welcome back. Hopefully you're okay after break with the coffee, with pizza and stuff. But yeah, we're going to continue this our session here. So okay, we described collecting tubules right here, but they're like gathering together into bigger structures you already know, and these bigger structures are called calyces. Calyces. It's buffering right now. Everything is okay. Most of them are saying everything is okay.
Yeah.
Yeah. So okay. So these collecting tubules are gathering together into calyces, and what we can see here in this slide. One thing I can say to you is that this slide is going to be on the oral exam. So yeah. So we're trying to make it more easier for you. So this is the slide that is going to be on the oral exam. So yeah, these were the collecting tubules that we described earlier. They are gathering together in the calyces, and what we can see right here is a small part of the calyx. So this big structure right here, the big hole right here, is a part of small calyx. And how I can differentiate it from the vessel? So also the big holes, there are big vessels, like here. Some of these are vessels. You can see it right here, the tissue and vessels there. But this hole here is calyx because it has got special epithelium on its surface. And you probably know the special epithelium that is all over the urinary system, and it's transitional epithelium. Transitional epithelium. Transitional epithelium. So it's like this. This is the basement membrane, and this is the transitional epithelium. And this epithelium is stratified. So it's normal stratified epithelium with big cells that are in the last layer here. These cells right there, big cells that are protruding into the lumen in here. We will describe them also later in the urinary bladder and ureter. And these cells are called umbrella cells. So this is very special epithelium for the urinary system. Transitional epithelium, stratified epithelium. So this structure right here, whole structure, is small calyx. We cannot see really big calyces here and the pelvis because these structures are too big for the light microscopy, so we can see the small calyx.
And we can see here near the calyx big
Yeah.
collecting ducts, which can be called papillary ducts.
So big.
of Bellini, which are lined with high columnar, simple columnar epithelium.
Okay, so big collecting ducts here, tubules, and also here is one big
Mm-hmm.
Bellini.
Mm-hmm.
Bellini. Okay. So, and you already asked about macula densa, yeah? So we're going.
Ten electronmicrograph teda
Yeah.
toho.
I'm sorry.
Maybe we can now look at the last electron micrograph because it is also collecting tubule or duct.
Yeah.
Me?
Yeah, you can
Yeah,
describe it.
okay, so when I started, you
starting,
can
and it-
see that there are about 3 cells in this picture. 2 of them are high, columnar, protrude to the lumen, have got small microvilli on the surface, have got some mitochondria inside, but not so many, so we guess that they should be light eosinophilic, and they are called clear cells. Yes, they are important for the water absorption because they have got in their membrane, in their apical membrane, aquaporins, which were already described by Andrea before a break. And we can see also one piece of a dark cell, which is also called intercalated cell. It is situated between clear cells and it touches the lumen only by a small area of its surface, and we can see that it has very many mitochondria. Of course, we don't see here nucleus, but it's normal because of section, so we can see only mitochondria here. These cells are very active and that's because they are transporting ions. They are transporting mostly hydrogen and bicarbonate ions.
Chloride, no?
Chloride ions as well, and bicarbonate ions, and also H plus.
Yeah.
They haven't got fully developed basal labyrinth, but they can transport ions. They are hardly visible in a light microscope because they are too small, but sometimes in high magnification we can catch them.
Yeah. But it's really not important to distinguish them in
yes,
a light
it
microscope.
It is difficult.
Yeah, so you don't have to worry about that.
Mm-hmm. Clear
cell. Is that mean as they are elucent or an actual formal name of the cells? It's normal formal name.
It's normal formal name, and this name is probably not from electron microscopy, but from their light microscopic light eosinophilia.
Okay. So right now, as we started the discussion about macula densa, you were asking about macula densa, where it's located. You know its important structure, and it's important structure of something called juxtaglomerular apparatus, and we're going to find some and describe it. Juxtaglomerular apparatus. I'm going to write it down, don't worry, but we're going back to the cortex to find some good apparatus. And I need a little help, probably there. Where was the good one? We were.
It isn't easy to say.
We're going to find some good to describe, maybe in a higher magnification. will be... It's not that good. We're sorry. You just have to wait for us to find some good one to... We're not very satisfied what we're seeing right here. Like, we can see it almost on... Yeah, maybe this.
Maybe. Yeah.
Okay. Yes. We found some.
It's good corpuscle with both poles.
Yeah. So we found something. And you know, the distal tubule is coming back to the renal body. So as we saw this picture here before, this distal tubule is going to back to the... It's going back to the renal body, to the vascular pole. So this is the vascular pole. These are the vessels that are going in. And the distal tubule is going to be like this, to the vascular pole of the body. And the cells which are lining the distal tubule are going to change. And we are going to describe it right now. I'm going back to the microscope. And so, for repetition, these are the proximal tubules around, highly eosinophilic tubules. This is the P, not D. P. And these are the distal tubules right here. This is one distal tubule. And this is another section for distal tubule. And this is a distal tubule right here. So the distal tubule is going back and it's going to connect with the vascular pole right here, vascular pole. And the cells which are lining the distal tubule, I'm sorry, this should be D, not P. The cells which are lining the distal tubule are going to change to cells which are called macula densa. Macula densa. I don't know if it's the right name also in English. Macula densa.
Yeah.
Dental macule. Like the dark spot, I guess the translation of this, the dark spot. And these are the cells, I guess, like I can write it down, like the first cells of apparatus called juxta glomerula apparatus 2P.
Yep.
Apparatus. So the macula densa is first part of the juxtaglomerular apparatus. The second cells, which are here in this black spot right there, the next cells are called, I'm going to write it on the somewhere here. The next cells are juxtaglomerular cells. Juxtaglomerular cells. And these cells are very special because these cells are actually smooth muscle cells from the arteries that are located in the vascular pole. From the wall of the, I'm writing down in the Czech, but smooth muscle cells. Yes, smooth muscle cells, which are from the arteries, from the afferent or efferent arterioles. You know that the wall of arterioles is made of smooth muscle cells. So juxtaglomerular cells are modified smooth muscle cells of the afferent and efferent arteriole that are located in the vascular pole. So there should be probably, I don't know how to really,
we can say that this lumen theoretically
This lumen right here
Can
probably.
be a lumen of one of these arterioles.
We don't know which one, but probably one of these arterioles. So the cells that are the closest to these arteriole right here, probably these cells right here, I guess. Yes?
Mhm.
These cells right here should be juxtaglomerular cells. Juxtaglomerular cells. So the modified smooth muscle cells of arterioles which are there. So we have macula densa, modified cells of the distal tubule, juxtaglomerular cells, and the third cells that are located in the juxtaglomerular apparatus are extraglomerular mesangial cells. And you already know mesangial cells because we described them earlier. But these cells are also like mesangial cells. They're the same, but they're located extraglomerularly. That means that they're like outside of the glomerulus right here. So these cells right here, okay? These are probably the extraglomerular cells right here. Maybe not like this last one, but these cells right here are extraglomerular mesangial cells, and they're doing their stuff. So they're doing the phagocytosis, they're doing the contractions, they're producing mesangial matrix right there. So these are the normal mesangial cells, just located extraglomerularly. That's why this like whole name, complicated name, that it's hard to like say.
Yep.
Okay, so and what's this thing for? Why do we have juxtaglomerular apparatus? Is that the juxtaglomerular apparatus, the juxtaglomerular cells, are producing enzyme called renin. And you're going to learn more about renin in physiology, but right now you should know renin is an enzyme which cleaves a protein called angiotensinogen. Angiotensinogen, it's protein, it's big protein, which is cleaved by renin, which is an enzyme produced by juxtaglomerular cells. And from angiotensinogen, we get something called angiotensin 1. And this protein is made of 10 units, amino acids.
So it's short peptide.
This 10? It's 10?
10?
Okay.
Maybe. Yeah.
Okay, and this short peptide is cleaved by angiotensin converting enzyme to angiotensin 2. And why is this important? Is that angiotensin 2 is going to raise blood pressure by constriction of the vessels. So the vessels are going to constrict because of angiotensin 2. And there, this enzyme, this peptide is also going to raise the levels of aldosterone. And you already know what aldosterone is doing. Aldosterone is like influencing, regulating, stimulating the pump in the distal tubule. So this is going to raise the blood pressure. And when the blood pressure is high, that is going to stimulate the macula densa. Right? The high levels of sodium in the blood are going to stimulate macula densa, and the macula densa is going to say, okay, stop, now we're done, our blood pressure is high, so stop. So macula densa is a big regulator in this process. It's going to say to juxtaglomerular cells that they need to stop to produce renin. So renin is going to raise the blood pressure, macula densa is going to react and lower the blood pressure. So that's why we have juxtaglomerular apparatus right here. And you don't really need to worry about that much to distinguish these cells. but it's very hard sometimes. You're not going to find a juxtaglomerular apparatus on each renal body.
It's impossible. It must be a body with a vascular pole visible.
Yeah. So, okay. But you need to know why is this for, how it is working. You're going to meet with that in next years. So, yes. Okay. And I think that's all for this slide. And now we're going to have a slide stained by PASS. So, please, doctor, will you explain the slide with PASS reaction?
So we can change, and if you help me with drawing,
Yes.
I can describe another slide. It's slide number 54, when you'll be able to study our slide boxes. You'll find it under this number. And you can see that the structure is the same. Here is the cortex of a kidney. Here is a medulla of the same organ. And what is here positive? PAS or PAS reaction is a histochemical reaction visualizing polysaccharides, complex molecules which are situated in basement membranes, for example, because basement membranes contain highly glycosylated collagen type 3. So PAS reaction is in this case showing collagen type 3 mainly. Of course, we can use it also in another slides where it will visualize mucus or cartilaginous matrix, but it isn't the case of kidney. When we look at the higher magnification, and we'll focus on some renal corpuscle, I put it to the center, we can see thick basement membrane around the parietal list or parietal layer of a Baumann's capsule. It's very thick basement membrane, and you can see that some thinner lines, thinner like basement membranes, are also in the renal corpuscle inside. They aren't full basement membranes, but they are just complexes of fused basal laminae, which you already saw in electron micrograph, for example. Basal laminae don't contain collagen type 3, but they contain another sugars like heparan sulfate. It belongs to glycosaminoglycan, so it's polysaccharide as well. So some PAS positivity is here, and dark spots or purple spots in the renal corpuscle are places of mesangial matrix. Mesangial matrix produced by mesangial cells is rich in collagen type 3 and other molecules which can be PAS positive. You can see similar but thinner basement membranes around all. Something happened, but it will surely improve. You can see thinner basement membranes, yes, here for example around this proximal tubule. Of course, in this staining we don't see eosinophilia because eosin isn't used here, but hematoxylin is here, so we can see nuclei. So I can be sure that it is a proximal tubule. We can see, because we can see only few nuclei. We can see long segments of a wall without any nucleus. And also we can see irregular luminal surface. where is brush border, and you can mention some pus positivity of brush border as well, because it's rich in glycoproteins, and these glycoproteins form here glycocalyx. Yes. Fine. So that's why we are using this staining, and you should know it. If we look at this slide in small magnification once more, we can see that it has the same structures as the previous one. Also, the vessels are here. Maybe I can find some renal calyx again with transitional epithelium, which was I lost it, but here it is. Yeah, and quite nice is a smooth muscle. Some smooth muscle is in the wall of this calyx as well, but much better smooth muscle is in the vascular wall, where we will see, wait a moment, I'll find some artery, or here is better, and we can see reticular fibers in the endomysium around each smooth muscle cell. Just repetition, it doesn't belong to description of a kidney, but you hopefully know it from basic histology. I see some question. I frequent this online discussion method for
discussion message board called Forge, and they have told me that urine is stored in the testicles. Is it true?
it's some nonsense.
Are you kidding?
I don't know skein or what's the pronunciation, but I hope he or she isn't our student. And Roxana is helping me that it is really nonsense. Testicles and urine haven't anything common. So let's go on. I think that we can leave this slide.
Yeah.
Of course, if you have it in examination, you can describe the same things as were described in the previous slide. So don't think that the hematoxin eosine kidney needs a long description, and pus kidney needs only short description of pus positivity. Yeah, I think that all structures, all tubules are here recognizable, like on the previous slide. Let's go to the ureter. So will we change again? Yeah. So Andrea is again ready to demonstrate ureter.
These are the last two slides for me, and the one last slide you're going to describe the last slide, and also development of the urinary system. So these are two last slides for me. First is ureter. Ureter, okay. I'm going to change this. Ureter is slide number 56. And you know, ureter itself is a small tubular structure, small organ. I can say it like organ, yeah, small tubular structure. And this is the cross section of the ureter. And you already know that the digestive system has its own structure of its wall, but the urinary system is somehow different, and we're now going to describe it. So this is the whole cross section, and you can see some lumen on the inside, and there is of course some mucosa with epithelium and some muscles around, smooth muscle cells around, and like loose connective tissue all around the ureter, and that is of course adventitia. Adventitia, yeah. Because we know ureter isn't located in the abdominal cavity, so adventitia is on its surface. And now we're going to look for the wall. So what are the main parts of the wall? Yeah, I'm going to put it like this. Yeah, I'm not asking many questions because there is some delay, so it's very not sufficient to ask something and wait for it like for 10 seconds. But so I'm describing. I'm not really used to that, so hope you guys are okay right now. And we're going to describe right now the main parts of the wall. So this is the ureter, and the first part right here, like this, is the mucosa. So this is the mucosa. Oh no, my brother. Once again, I'm pushing some buttons. I don't know about them. Okay, so mucosa. This is the mucosa, and also mucosa have some parts. We're going to describe them later. But this is the mucosa, and right here under the mucosa, we're do not have submucosa, so don't describe submucosa in the urinary system because it's not there. There's just only mucosa, which is made of epithelium and loose connective tissue or lamina propria under the epithelium. So we don't have submucosa here, but right under the mucosa we have smooth muscle cells, which are organized into some layers, smooth muscle cells. And this is the muscularis. Muscularis. The main muscular layer of the wall. And right after the muscularis, we have loose connective tissue, and this is adventitia. So these are the main structures of the wall: mucosa, muscularis, and adventitia. So right now we are going to focus on mucosa. The slide number 56. Slide number 56. Okay, and now we're going to focus on mucosa. Yay! So it's quite pretty. So once again, the mucosa is this part right here. We can see some smooth muscle cells right here. So this is already a part of muscularis right here. This is the muscularis starting right there. And this is mucosa. And mucosa contains of what C, a small C here, but you can understand. Mucosa consists of epithelium on its surface. So epithelium here, and you already know this epithelium is transitional epithelium or urothelium transitional. You already know this epithelium. We described it in the calyx of the kidney. But right here, we're going to focus a little bit more on it. Hopefully, we can see some pretty umbrella cells here. I can see them already. I'm looking for some. Okay, I'm not able to find prettier ones, but yes, the apical cells here are umbrella cells. These are pretty much quite good umbrella cells here. Yes, umbrella cells. Yep, so normal transitional epithelium. Right under epithelium there is a loose connective tissue of lamina propria, and you can see some vessels there. So there are some vessels, and yes, of course, some cells, fibroblasts, and some inflammatory cells probably they're just hanging around and watching stuff, and collagen fibers, of course. So these are the collagen fibers right here, if you see them, collagen fibers. We can see longitudinal sections of collagen fibers, cross sections of collagen fibers. So this is like that. So mucosa, just normal mucosa. The epithelium is kind of different, but it's typical for urinary system. So yeah, that's all. What about muscularis? Is that it has some parts. You know from the digestive system that the first layer, which is close to mucosa or submucosa in the digestive system, is circular. This is kind of different in urinary system because the first layer right here is longitudinal. This is the longitudinal layer right here. And the second layer, which is right here, is circular layer. You can see the longitudinal sections of the smooth muscle cells. Smooth muscle cells are arranged circularly around the ureter. So this is the second circular layer. So the first is longitudinal, the second is circular. We can see that the smooth muscle cells here, there is a cross section through smooth muscle cell. So this is the longitudinal layer, first layer. And sometimes when you're going deeper or down to the ureter, yeah, almost close to the urinary bladder. So this is, oh, okay, it's pink. It's going to be pink. This is the ureter, and it's going to the urinary bladder right here, and the second ureter. So in this part right here, oral part, I guess, cranial part, a cranial part, there are only 2 layers of muscularis, but in the part close to bladder, there are 3 layers. So sometimes in other slides, you can see another layer right here, right after the circular layer. There would be cross sections of smooth muscle cells, and that is going to be 3rd layer, also longitudinal. Yes? So don't worry about it. Sometimes you find slides with 2 layers, sometimes you find slides with 3 layers, but that is completely normal. That is just like how things work for the ureter. So when it's close to urinary bladder, there are going to be 3 layers. The first one is longitudinal, then it's circular, and then it's also longitudinal. We can see only 2 layers here in this section. Yeah, only 2 layers. And yeah, that's probably all. This is adventitia around. So we cannot see mesothelium or stuff like that. This is just loose connective tissue that is connecting with the other loose connective tissue around the ureter. So this is just adventitia. Yeah, you can see some vessels here, probably adipocytes and stuff, but yeah, this is typical adventitia. So I hope that is clear. That's everything from this slide. It's pretty easy, so you don't want to mess that up. There are not much things to describe here, but you need to remember the basic layers of the ureter. It's mucosa, then it's muscularis and adventitia on the surface. And if you're not going to mess that up, it's going to be pretty much okay. The next slide is urinary bladder. It's slide number 57. Yes. The slide number 57 is urinary bladder. And you already can see, I just put it in the under the microscope, and you can already see, too much smooth muscle cells here. Okay, so this is probably the muscularis also. And yeah, okay, this is the surface that is right next to the lumen. So, okay, this is the lumen of the urinary bladder, and this is the surface. And the situation is going to be the same. we have also the mucosa, the muscularies, and some parts contain. Oh, it's telephone ringing. We're sorry about that. We have mucosa, muscularies, and serosa, and in some parts of the bladder adventitia, because the bladder, it's covered by the layer of peritoneum on its like the upper portion. It's covered by peritoneum, so sometimes we're going to find serosa most of the time, sometimes adventitia, but in most cases you should be able to find serosa. But yeah, so let's describe these layers here. So once again, we can see a mucosa right here. And it's really the same. The difference isn't that much here. There is an urothelium on its surface. Maybe we can check that. Urothelium. Hello there, urothelium. Right here. Ooh. Urothelium. These are the umbrella cells. This is pretty much like this already. This is pretty urothelium. And okay, and the lamina propria is once again under the epithelium. So we have a lamina propria under the epithelium. So this is basically the same like in a ureter. Yes, this is the mucosa. And right now we can see a smooth muscle cell starting right here, and this is the muscularis layer. So this is where it's going to start, the muscularis layer. In this case, muscularis is divided into 3 layers. I'm going to... Okay. So, 3 layers, and the first layer of the muscularis here. So this is all the muscularis right there, and the first layer of muscularis is plexiform layer. So it's not really arranged like normally, I guess. It's a net. It's somehow like mixed together as the cells. It's plexiform layer. It looked kind of circular, but it's really just a net of smooth muscle cells. This is the first layer, plexiform. The second layer, after the plexiform layer, is circular layer. And it's going right to the end. So the next layer is circular layer. I'm going to write that down for you. Circular. Okay, that's quite correct. So the first is plexiform, then is circular layer, and the last one, the last layer is supposed to be longitudinal layer. But in this section, the urinary bladder is kind of thick. The muscularis layer is thick. So right here, what we can see is this plexiform layer right here. There's just thin layer here. And this whole smooth muscle cells here, here, here. This is almost all the circular layer. And we can see right here that is an artificial cut. So, yeah, we're basically not able to see longitudinal layer itself. So the muscularis of the bladder is too thick for our light microscopy. So there's just artificial cut, and we are not able to see serosa on its surface. So it's going to end with the muscularis, and yeah, we don't really have nothing much more to see right now. So sad. We cannot see serosa here, only the 2 layers of muscularis. I hope that's okay. Do you understand me? Do you understand everything that I said? And if there are some questions, ask them now. We have some time to discuss right now. I think this slide is kind of simple. If you compare kidney with this slide of the urinary bladder and with the slide of the ureter before, like which one do you want for the oral exam? Like, of course, ureter. But yeah, that's how life goes, and maybe you're not going to be that lucky and you're going to choose kidney. But kidney is more interesting and prettier, I guess. So if you have some questions right now, ask them right now. So don't mess the wall, the parts of the wall. Don't forget that urinary system doesn't contain submucosa and stuff. Look, Lucas, is there something important to say for serosa? Well, not so much. Like serosa is the same like all serosa in the digestive system, which is in the peritoneal cavity. So serosa is just like the part made of loose connective tissue with simple squamous epithelium and mesothelium on its surface. So it's just loose connective tissue. Probably there are some adipocytes in there, the vestibulus and mesothelium. So, and the next question, no, no. They're asking me if I'm single. No, I'm not single. There's a Professor Catholic here. It is shown you our lecture. It's shown on our lecture. Okay, so this is all thing about the slide about urinary bladder. So hopefully you're okay with that. And the next slide, I don't know if we're going to describe it or should I? We're going to change right now. Okay, so the next slide is penis. And I'm going to just draw a thing right now. Probably on anatomy, you have a picture you have to write. It's like the urinary bladder like this, urinary bladder. Then it's a prostate right under the urinary bladder. Then it's like diaphragm. And then it's the penis right here. So this is how it looks like. I don't know if you already know this picture. It's compulsory? Yeah? No? So, yeah, I'm sorry. I'm not drawing like very much pretty. This is not how the penis looks like, but okay, it's something like that. And there is like the skin and stuff. Okay. And we already had a section through the urinary bladder. Yeah, we had the section, and we're going to have a section through penis. And there are some parts of the penis like the spongiosa part or the urethra, which is going through corpus spongiosum, like in here. And also we're going to have a slide. I don't know if there are some slides that are containing
these. Some slides are through the body of the penis and some are through the glands.
Through the glands. Yeah. So there are going to be different there is going to be different epithelium in the urethra. You know, urinary bladder contains transitional epithelium, but urethra in the penis right here in the body of the penis is going to contain is going to like it's lined by stratified columnar epithelium. And here in fossa navicular fossa, I don't know if it's the same in English. Yeah. Navicular fossa, thank you. It's going to be squamous stratified epithelium. So right now we're going to look on the penis and urethra that is going through the penis. That is slide number.
Let's take it first this one and then.
Okay,
so we can change. So we are changing once more, and I am looking for an urethra. Penis has got also corpora cavernosa. Theoretically there should be skin on the surface, but it isn't on our slides. We'll look at the specimen once more in the male reproductive system. So I would like to focus today only to corpus spongiosum, yes, which I already found, where we can see male urethra. I lost Andrea, so there is no problem with drawing, but I will show just by the mouse that this is urethral lumen, and here is the epithelium. Around is corpus spongiosum, urethra, where you can find quite big spaces filled with erythrocytes. These are venous cavernous spaces, and we'll describe them in the male reproductive system. In between, you can see some smooth muscle tissue which belongs to the wall of the urethra, because urethra has got also tunica mucosa from epithelium to this level approximately. Sorry for this very rough drawing, I have two rough hands. And here is tunica muscularis. That means these cavernous spaces can be found in both these layers. Now let's focus to the epithelium. I remove drawings, and you can see that this epithelium differs from the epithelium of bladder or ureter or calyx, which you already saw, because it isn't transitional epithelium, but it is really stratified columnar epithelium, quite rare epithelium, which is found in some big ducts of salivary glands, for example, and also here in the spongious part of the male urethra. So you can see high and narrow cells which are really columnar, and these cells are in the superficial layer of this multi-layered or stratified epithelium. And when I'll go along this epithelium, I can sometimes find such lighter spots. Where are another cells? Or here, these are groups of mucous cells. I think that, for example, here down, it's easy to recognize that they are really mucous cells. They have basal dark nuclei and light apical cytoplasm. If I increase them, we can see. I try to give them to this circle once more. We can see granules, light, translucent granules, and these groups of mucous cells in the epithelium are special intraepithelial glands, which are called, I don't know if I'm able to write it, that they are called urethral, oh, it's terrible, urethral, just lacunae, urethral lacunae, point, urethral lacunae of Morgan. You must help me. It's quite good, isn't it?
Good.
Yeah. Urethral lacunae are already described, I think. And
Yes,
now we'll go back to Now we'll go back to small magnification, and we'll look for another mucous glands, which are not intraepithelial, but are situated in mucosa and can penetrate between cavernous spaces into muscularis, and they are called paraurethral glands of Litre. Paraurethral glands of Litre. They are also mucus. They are secreting the same type of mucus as the intraepithelial lacunae. Glands. Paraurethral glands. Almost. Of yeah, it's okay. Of Litre, double T is there.
Of Litre.
Yes, it is. Yes, okay.
The glands of Litre.
Glands of Litre.
And this is another one here.
Yeah, another one.
Yes, one. Okay.
And as Andrea already described, there is possible to find another sections of penis in our boxes, which are made through the terminal part of penis, through the glans penis. And again, I'll try to find only urethra at this moment, so give me short time. Again, no skin is here on the surface, just some subcutaneous tissue and cavernous bodies. And here is terribly damaged, but is here a part of urethra, where is stratified squamous epithelium. I hope that I'll find some segment where I really able to show that this epithelium is squamous. Maybe here. And we can find litres paraurethral glands around the urethra as well. For example, here, or maybe better is more magnification. Yeah, litres glands are here, but Morgan's lacunae are not developing in the squamous epithelium. They are only in this part where is columnar epithelium. So there are two possibilities of the slide of penis and urethra.
Now, how is that? I can see that there is a columnar epithelium, like here.
It is a piece with columnar epithelium and litres.
Yeah.
I guess that it is a litres gland and it's a beginning of its duct.
But these aren't the like intraepithelial.
It's like Morgan's lacuna, but as it is not in the main lumen of the urethra, it must be a gland.
Okay.
Yeah?
Yes. Mm-hmm.
Fine. Okay. And that's the last slide. So it is the end of histological part of this lesson. And so let's go to embryology.
Yay! Okay.
yeah. So I have to.
Daj si to pero. Šipku stlač.
Šipku.
Okay.
Aha.
Sorry about that.
Okay,
I'm very
sorry. And we don't need this,
Oh.
and we don't need.
Yes.
Aha. Minimize. No.
Okay. Once again.
Once again, and why there isn't this studio? But we don't need it.
No, we don't need it.
We
just
need urinary system development. So
Yes.
I'll use for this purpose a video file.
Yeah.
Urinary system development.
I'm just going to say we're not going to be able to see chat right now, but I'm going to read it on the next computer, so don't hesitate to ask some questions. We're going to answer them. So I'm going to just ask them ask the doctor to answer the questions.
Yeah,
so just write the questions.
Okay. Sorry, one technical break.
Yeah.
Yeah. Okay. So you can see that the beginning of this file, which you can find also on Moodle, or you can download it from another place of the internet because it's free, and it's based on the very good textbook from Professor Larsen. This video file is beginning by formation of the urinary system and formation of the nephrogenic cord. So where we are in the 20th day of the development. That means near the end of the 3rd week of the development. You already know that the embryo is in the phase of free laminar germ disc, and it just developing neural plate with its groove and fold, but it isn't important for our purpose. It's just in which stage the development is. So I'll go on, and we will see cross section through the trilaminar germ disc. You can see that this trilaminar germ disc has got ectoderm upstairs, endoderm down. Ectoderm is developing neural tissue, neural groove, neural crest is here developing. Here is a notochord, which has got still its lumen because it's very young stage of its development, and we are mostly interested in mesoderm now. When I stop it with these labels, we can see paraxial mesoderm, intermediate mesoderm, and lateral plate mesoderm. Paraxial mesoderm was already used for the development of vertebral column, muscles. You know it from previous semester. Lateral plate was also used for development of intraembryonic cavity, intraembryonic coelom, and what we still didn't use so much is this middle part of the mesoderm, which is called intermediate mesoderm. But today we'll need it very much. So let's look at the formation of tubular embryo. There will be folding. So we are leaving the 20th day, and we are going to the 4th week of the development, and we can see how the proportions are changing. The flat germ disc changes to the tubular structure, tubular embryo. Here, maybe I can send it once more. Many new structures are developing. The neural groove is changing to neural tube. Roof of the yolk sac is changing to the intestinal tube, to the gut. Dorsal aorta is developing by fusion of two dorsal aortae. You can look at this movie once more and you will see it. Chorda is losing its lumen, and our intermediate mesoderm, which is here, these two light pink circles, is changing as well. And when I'll finish this sequence, we will see how this intermediate mesoderm is forming something which is called nephrogenic cord. We are at the end of the 4th week, and nephrogenic cords were developed from the intermediate mesoderm in both sides of the abdominal and thoracic, so intraembryonic cavity, intraembryonic coelom. Here is the gut, and here is also liver developing at this section. But for us, it's interesting, this dorsal aorta, we will need it for the kidney development, and these two cords which are protruding quite deeply to the abdominal or thoracic cavity, which are not separated at this moment. And it is the end of the 4th week. Now we can look at the detail of this nephrogenic cord. Now it's better. And we can see that something is situated inside, and it is structure which can be called primitive nephron. So the intermediate mesoderm, the tissue of the intermediate mesoderm, develops into epithelium. It is so-called mesenchymo epithelial transition, and nephrons are developing. And not only nephrons are developing in this nephrogenic cords, but also vessels are growing inside to give rise to glomeruli, but it will be later. Now we are seeing whole embryo during the 4th week, which is just folding, and we can see yellow nephrogenic cords, and here cranially at the level of cervical segments, these cords are segmented. You can see small like chain-like structures, segments of the nephrogenic cord. These segments here are called nephrotomes, but they are developing really only in the cervical region. Thoracic, lumbal and sacral part of the nephrogenic cord remains unsegmented and can be called nephrogenic blastem. So nephrogenic cord is dividing into segment nephrotomes cranially and a much longer nephrogenic blastem in the remaining length of them. Here downstairs is cloaca. We'll need it as well. You already know that cloaca is a blind end of the gut, of the hind gut, where also allantois is going. We will need it for the formation of other parts of the urinary system. Now we will see how this nephrogenic cord is changing. We'll start in this cranial area. Nephrotomes situated at the level of cervical somites don't develop into functional units in human embryo, but they are important for the further development of the urinary system because they form a very primitive kidney which is called pronephros. Pronephros doesn't form urine, it doesn't work, but it's inducing formation of pronephric duct in the intermediate mesoderm, a little bit more dorsally. This pronephric duct grows towards the caudal end of the embryo, and during this growth it induces formation of the next part of the kidney, or next generation of the kidney, which is called mesonephros. Mesonephroi is plural, so we have got two mesonephroi, one and second mesonephros. This pronephric duct is changing its name into mesonephric duct, but it's still the same duct, and mesonephric duct wouldn't develop without the earlier formation of pronephric duct. This mesonephric duct is very quickly growing. You can see that it is the 24th day, and when I send it, when I let it go, we will see how quickly it's growing, and it's growing towards the cloaca. And during its growth, it's inducing formation of nephrons in the mesonephric part of the nephrogenic blastem. The number of these new mesonephric nephrons is a little variable, but it's between 40 to 42. At the level of each somite, about 2 or 3 new mesonephric nephrons are developing. And you can see that the beginning of mesonephros formation was 24th day, and now there is 28th day, and full mesonephros is developed. So during 4 days, so long structure was developed. We have about 40 new nephrons in both sides, and our duct, this mesonephric duct, is finished in the cloaca. We will see a detail of the mesonephric system. There is a duct, there is a tubule which has a S-like shape. It is dilated at the end to form something like Bowman's capsule, and glomerulus is developing as a branch of dorsal aorta. That's why we need it. At this moment there are still paired dorsal aortae, and glomeruli or branches these aortae are growing towards the Bowman's capsule and are forming glomeruli. So this system can work, Urine which is produced by this nephron is collected by mesonephric duct and drained to cloaca. Cloaca is blind at this moment, but it can fill with urine. We'll go on. We are at the end of the 3rd week and we have a working mesonephric kidney, but it is not the end of the kidney development. Our definitive kidney doesn't develop from mesonephros. Mesonephros can work, it starts its work during the 5th week, but it disappears and stops its work during the 10th week, so it's only temporary structure. Definitive kidney is developing from the sacral part of the nephrogenic cord, which is called metanephros. How is it developing? Here is this brown snail. This brown snail is a ureteric bud. Ureteric bud or ureteric diverticle, or also metanephric diverticle, which is a branch of the terminal end of mesonephric duct. So it develops from the same tissue, from the same source as a mesonephric duct, that means still from the intermediate mesoderm. And this metanephric or ureteric diverticle or bud is growing to the tissue of metanephros, which is waiting, which doesn't do anything. We will see what this ureteric or metanephric diverticle is doing. It's branching, and it doesn't branch only once, it branches many times, and during this branching it forms pelvis, it forms calyces, and at the end it forms collecting tubules and ducts. As there is about 1 million of nephrons in each kidney, we must say that there is at least 1 million of these terminal branches of collecting system. And if I well remember, Andrea said in the first part of this lesson that collecting system, collecting tubules and ducts and nephrons have got different embryological origin. So here it is. Collecting ducts and tubules develop from the ureteric bud, and nephron is developing from the surrounding metanephric blastem. Both these structures develop from the intermediate mesoderm, but little differently. So now how does the collecting tubule stimulate the surrounding tissue? We will look at the small part of metanephric blastem. We can see terminal branches of ureteric bud, future collecting tubules, and we can see surrounding cells which were originally dispersed mesenchymal, and now they are organizing to form some epithelial structures. At first just small vesicles which are called renal vesicles. These renal vesicles elongate, they become tubules, it will be in a moment, tubules, and they join the collecting ducts. So this gives rise to S-shaped tubules, future nephrons, which have got a part developing from the metanephric blastem and a part developing this part is joining the collecting system. I don't see now if there are any questions, so wait a moment, I look at it. No, there isn't any new discussion. So this is another view to the developing nephron, and we'll go to we'll go to another parts of this video. Relocation of kidneys. As I already said, kidneys are developing from the caudal end of the urogenital ridge or of this nephrogenic blastem, and we know, and you know from anatomy, that the definitive kidneys are situated in the upper lumbar area. So it has to ascend, it has to relocate, and during this relocation, it will be well visible in this sequence, they change their vascular supply. They are moving along the aorta and they receive new branches of aorta, new arteries, of course also veins which aren't visible in this video, and so the definitive renal arteries are completely different vessels than the original renal arteries which were growing from iliac arteries. It's this ascent of kidneys is at the same time as the descent of gonads, which we'll describe next week. And now the last part of this video, I promise last 10 minutes probably of this program, is a development of cloaca. So as I already said, cloaca is the terminal end of the hindgut, which is connected to the allantois. Allantois is a blind sac going to the connecting stalk. So the structure of the cloaca is quite complicated, and we know that mesonephric ducts were growing and are now open to the cloaca, and they developed also metanephric diverticulum. So there are two structures going to the cloaca because cloaca is increasing, and so the terminal end of both these ducts is incorporated into its wall. Cloaca has to divide into two parts. This dorsal part will give rise to terminal end of the digestive tube, that means anorectal canal. This ventral part is developing into urinary bladder and other parts of urinary and also reproductive passages, and it's called urogenital sinus. Septum, which is dividing these two structures, is developing here. It's called urorectal septum, and you will see how is it forming. Here it's written urorectal septum. It's growing caudally, and you can see that at this moment cloaca is still closed. There is still cloacal membrane, but during formation of this urorectal septum, this cloacal membrane disappears, and both parts, that means urogenital sinus and anorectal canal or channel, are now open to the amniotic cavity. This happens at the end of 7th or at the beginning of the 8th week of development. So much later than this rupture and disappearance of oropharyngeal membrane, which was already during the 4th week. And you can see anorectal channel and urogenital sinus with separated end of mesonephric duct and ureteric or metanephric diverticle. Urogenital sinus will now we are interested in this part. Let's finish description of the anorectal channel, and we will see that urogenital sinus or has got three parts. It has got vesical part, which gives rise to urinary bladder, pelvic part, and phallic part, which develop differently in males and female. Now you can see it was 7th week, so there was still urogenital membrane, and here is 9th week. Probably here urogenital membrane is disrupted. Urogenital sinus is growing and is, as I already said, incorporating terminal ends of our mesonephric duct and ureteric bud. And these two structures will participate in the formation of its wall and together form so-called trigonum vesicae, which you probably know from anatomy. Sorry, I'm a little bit lost now, but yeah, here is trigonum vesicae, where a wall of a urinary bladder develops from the intermediate mesoderm, because it was a tissue of the mesonephric duct and ureteric bud. The other parts of the urinary bladder are developing from endoderm, that means epithelium is endodermal, and lateral plate mesoderm, which gives rise to other tissues of its wall, muscle, connective tissue, as you saw in the slide. And the last part of this video file will be development of urethra at first. Male urethra, which is much longer, so it needs both pelvic and phallic part of the urogenital sinus. Pelvic part gives rise to its prostatic and diaphragmatic portion, and phallic part gives rise to the pars spongiosa of the urethra and also fossa navicularis at its end. On the other hand, female urethra is much shorter, so it needs only pelvic part. You will see it. Now, here in this area, female urethra is developing, and instead of the spongious part, vestibulum vaginae is developing, so the spongious part of urogenital sinus is transforming into the vaginal vestibule in females, and also a part of vagina is developing from this, but it will be also next week in the development of reproductive system. According to my meaning, it's everything. Andrea, are here any questions? No, so everybody is tired or dead or something like this. So thank you for attention. You can look at this video on the same place once more or second more, how many times do you want. Share it with your friends, with your colleagues, and if you have some question which can come later, you can write them by email. Yeah, the chat will finish now, but email comments are possible, but I would rather see it in email because I am looking every day to my email and not to fix it comments. So
there is a question: if the schools are closed longer, are we going to take histology credit tests from home or once we get back?
It's too early to these questions. Of course, we'll reduce our program. Probably the second test, the middle test, can be cancelled, but it's too early for this question. Wait, you'll get all necessary information in next online stream or by email. I plan the next online stream next Thursday at the same time about male reproductive system. Maybe we can add some extra lessons as well, but this is my plan now. Go on like we are in school. So this week was urinary system, next week male reproductive. We will see how long it is necessary. So, bye. Pustím, jo, moment, Andrea probably wants to tell you goodbye as well.
There is a question once again if the stream is going to be posted in this channel. Yes, of course, you can find it on our channel. But okay, I think that's all. And goodbye. Don't forget to subscribe to our channel. And as you can see, we're posting videos, English videos about basic histology and also basic pathology on our channel. So you would probably want to watch that later. Okay, bye bye.